Hello, AP Physics. This is my first shot at creating a video in Zoom, seeing how it goes. This will be your review video for our next test, which is rotational motion, which will be our last test of the year. After this, it's all review, because the AP decided to get rid of the last 3 units of the year due to the coronavirus. So here you go. I'm going to try to go over the most important understandings, back to the equations, back to the context you need to think about them in. So let me go over to my document camera. This sheet should look familiar to you. We filled it out earlier, right before we left. It looks at translational equations versus the rotational form. The key with rotational motion is never forget how you use these equations and what the context were. For example, V equals d divided by t. Velocity equals distance or change in or displacement divided by time. Now I have omega, angular velocity, equals theta, angular distance or displacement divided by time. Context. Well, our context here is that we had constant velocity. So what do you think the context here? Constant angular velocity. Acceleration equals 0. Angular acceleration equals 0. Let's continue. Our next 3 equations can all be grouped together. If you remember the context of these equations, these were all constant. These are all constant acceleration equations. So what are these going to be? Well, of course, constant angular acceleration equations. Alpha equals change in omega over time. Angular acceleration equals the change in angular velocity over time. Theta equals 1/2 alpha t squared plus omega I t. Angular displacement equals 1/2 angular acceleration times time squared plus omega initial times by time. Omega f squared equals omega I squared plus 2 alpha theta. All constant angular acceleration. These were constant acceleration equations. So let me kind of place a line to block these equations out for us and the context we need to be aware of. Going down, we had these equations. So kinetic energy equals 1/2 mv squared. Well, kinetic energy equals 1/2 I rotational inertia omega squared. Momentum equals mass times velocity. Now, what do we have? Angular momentum equals I rotational inertia times by angular velocity. Change in momentum equals F times T. Change in angular momentum equals torque times time. Acceleration equals F net m, or its common form of F equals ma, Newton's second law. Alpha equals net torque divided by I. I'd like to connect kind of two equations for your understanding. And it's this equation here. When we provide a net torque, we create an acceleration. We are usually creating a constant acceleration that allows us to use these equations. So a lot of what you're going to do is a back and forth between these equations. And of course, the Newton's second law version relating to rotation. What other equations are important? Well, understanding what rotational inertia is. Rotational inertia equals the sum of the mass times by radius squared. So it matters what the mass is and where that mass is in according to its radius. Remember that we often think about this object that is a ring that has all of its mass on the outside. For that ring object, I equals mr squared because all of the mass is at the radius. Most other objects are going to have an I that's lower. You get a lower I by adding some fraction right here. And what other equation do we have? We have torque equals RF sine theta. Torque equals radius times force times by the sine of the angle between them. Again, you're going to see a lot of times this equation being used right in here to look at angular acceleration. So I recommend when you're doing your FRQs coming up, have this sheet out. Have your translational next to your rotational understandings. I want to do one other thing, and that's look at the situation of, let's say we have a ramp. Draw a ramp. And on that ramp, we have a wheel. It's important to be able to draw the forces on this wheel. On this wheel is always going to be, of course, rolling without slipping. The reason being, we can use our other important understandings. The velocity is always going to equal the r times our angular velocity. Acceleration is going to equal r times our angular acceleration. These equations allow us to go from rotational understandings to translational understandings in these problems. Well, let's look at our diagram here. What we have to realize is that all objects in physics we're going to talk about, we talk about this place called the center of mass. Usually for us, we're looking at symmetrical objects. That center of mass is always going to be in the center. Coming from that center, we have the force due to gravity. Because this force is acting on the center of mass, it actually provides no torque, and that's going to be important. You also, from the surface, have the normal force. And I'm just going to read from your book a second about the normal force in this situation. The normal force is exerted along a line that passes through the center of mass. So its lever arm is also 0, and it exerts no torque. So in this situation, we have force due to gravity providing no torque, normal force providing no torque. So where is the torque coming from? Well, it's from this last force. And that's the force due to static friction. So in this problem with our rotating wheel, we're always going to be interested in really this component. We may have to look at these to be able to understand friction, but this is actually what's providing the torque when we come to our torque equation. So I'm going to stop this video here. I think this understanding, along with your equations, are particularly important. Also on Monday, I plan on being available to work out some problems with people before we take out our test.